Here is a two-voice canon composed by Beethoven. This canon has repeat signs, making it an infinite or perpetual canon. Just as with any canon, Beethoven composes something for the leading voice, the proposta, la, sol, fa, mi, re, do, and then passes that along to the risposta voice. The interval of entrance for this canon is the unison, so the notes are not transposed, and the distance of entrance is 2 measures. In order for the canon to repeat, this bit of leading material that I've placed in a blue box must also be written in the last 2 measures of the proposta voice. If we want measure 10 to lead correctly back into measure 3, in the same way that measures 1 and 2 did, then we are committed to having those notes there in the proposta. Notice that Beethoven chose to have 8 repeating measures within the body of the canon, and that 8 is a multiple of 2, which was the distance of entrance. It is possible to compose an infinite canon where the body of the canon is not a multiple of the distance of entrance, but it can be much more complicated, and I will not be covering that in this video. If you're interested in learning more about that kind of infinite canon, I would recommend the books by Taneev and Norden, linked in the description. The key thing to understand about infinite canons is that the placement of the repeat signs is largely arbitrary. I could have written out all of the repeated music, or shifted the repeat signs 1 or more measures to the right, and our ears would not be able to tell the difference. This has consequences for how we think of the distance of entrance of any infinite canon. For instance, I just mentioned that this canon has a distance of entrance of 2 measures. But Beethoven could just as easily have turned the canon inside out, so to speak, by leading with the lower voice, and then the upper voice would follow at a distance of 6 measures. In other words, the key thing about an infinite canon is that it is a canon that works at 2 distances of entrance instead of only 1. I need to give a name to this other distance of entrance because I will refer to it often enough throughout this video, so I will call it the shadow distance of entrance. For the next step, Beethoven could compose anything he wants that works against the notes of the risposta in measures 3 and 4. Much like composing florid counterpoint against a cantus firmus. And that proposta material will then be transposed by the interval and distance of entrance to form the notes of the risposta voice in measures 5 and 6. This is what Beethoven came up with. Now we can simply rinse and repeat the same process for the next section of music. So far, this has all been pretty much the same conveyor belt method for composing finite canons that we looked at in the previous video in the series. However, when we get to composing notes for the proposta within this red box, we run into a problem that is unique to infinite canons. Whatever we compose inside of the red box must work in correct 2-voice counterpoint above the orange box in measures 7 and 8, and also below the blue box in measures 9 and 10. So, this material is going to be doubly constrained by pre-composed material and will require some form of movable counterpoint. This can be easily solved using an imaginary voice. We can shift the notes of the blue box back 2 measures and write them in within the orange box. I place those new notes in parentheses to indicate that they belong to an imaginary voice. Now that we can see the constraining voices vertically aligned, it is much easier to come up with something in the proposta voice in measures 7 and 8 that works against both constraining voices independently. If I seem to be moving too quickly, all of this can be reviewed in the 3rd video in this series on imaginary voices. In this case, because this 2-voice canon is written at the unison, we only needed to make use of horizontal shifting counterpoint. But with canons with a different interval of entrance, the problem becomes one of double shifting counterpoint, as we will see in the next example. But every infinite canon will eventually need to make use of some form of movable counterpoint in order to make both its distance of entrance and its shadow distance of entrance work, or in other words, to have a successful repeat. Here is a slightly more complex three-voice example composed by Haydn. Before we look at how the repeats are accomplished, we should review how a simple three-voice canon works, and again, this is review from a previous video. There are two combinations that have a distance of entrance of one measure. P and R1 is a canon at the upper fifth, and R1 and R2 form a canon at the lower 11th. These two canonic combinations can be thought of as an original and derivative combination related by vertical shifting counterpoint. The P and R2 combination is a canon at the lower seventh at a unique distance of entrance of two measures. To find the vertical shift index that relates the two canons in the first column, we use Taneev's equation JV equals n minus m, where the vertical shift index is the interval of entrance from the derivative minus the interval of entrance from the original. M therefore equals 4, since a fifth is 4 steps of the scale, and n equals negative 10, since a lower 11th is 10 steps of the scale in the opposite direction from that of the original. Plugging that into our equation gives us JV equals negative 10 minus 4, which is negative 14. This tells us that the original P and R1 combination must be composed according to the rules of invertible counterpoint at the 15th, which is effectively the same as invertible counterpoint at the octave. Before moving on, we should also consider how the repeats will affect this table of distances of entrance, since, as we mentioned earlier, infinite canons need to work at more than one distance of entrance in order to repeat. A formula for figuring out the shadow distance of entrance is the number of measures in the repeating body of the canon minus the distance of entrance. In this case, there are 6 measures between the repeat signs, so our two combinations that work at a distance of 1 measure must also work at a distance of 5 measures, and the P and R2 canon that works at a distance of 2 measures must also work at a distance of 4. In this example, these observations do not change our analysis, but we will see in the last example of this video how the shadow distances can become very important. Now, if we apply our conveyor belt analysis to the P and R1 combination, we can quickly see that the doubly constrained section is here in the red boxes of measures 6 and 7. The red material must work below orange and above purple. We are again going to use the trick of an imaginary voice. In this case, the interval of entrance is up a fifth, and we will need to undo that by transposing the notes from the purple box down a fifth to find the notes of our imaginary voice. Haydn's choice of the note E for beats 2 and 3 in the red box in measure 6 forms consonant intervals of a tenth below and a sixth above the two voices in the orange box. These intervals also happen to work well according to the rules of invertible counterpoint at the octave that we mentioned govern this combination. Now that we know that the P and R1 combination will successfully repeat, we do not need to repeat the analysis for the derivative R1 and R2 combination, since it is a copy of the canon we just analyzed. In fact, we only need to do this kind of conveyor belt analysis once for each distance of entrance in the table. If one canon in a column successfully repeats, the others will too, and this simplifies the amount of work we need to do to compose infinite canons. However, there is one more column that we have yet to analyze, and we need to check that the P and R2 canon at a distance of 2 measures forms a correct repeat. In this case, the red box needs to work above green and below blue. The notes of the blue box need to be shifted back 2 measures and transposed up a seventh. Those notes are pretty high up, so I've chosen to pencil them in the R1 voice instead of R2 in order to use the treble clef. Notice also Haydn's frequent use of rests, which prevent the voice leading constraints from piling up and becoming unmanageable. Lastly, here is an example of a 4-voice infinite canon by Mozart. Just like with the Haydn example, I'm going to analyze the relationships of the original and derivative combinations first, and then we will worry about how the canon repeats. In this case, there are 3 canons at a distance of entrance of 3 measures, 2 canons at a distance of 6 measures, and 1 canon at a distance of 9. P and R1 is a canon at the lower second, and so M equals 1 step of the scale. R1 and R2 is a canon at the lower ninth, and so N equals 8. 8 minus 1 is 7, and so this combination is governed by JV equals positive 7. R2 and R3 is also a canon at the lower ninth, and so it is also governed by JV equals 7. This is one of the easiest vertical shift indices, since the derivative is just the original counterpoint plus 1 octave. Both of the canons at 6 measures distance are canons at the lower tenth, and so JV equals 0 for this column. There are 12 measures between the repeat signs in this canon, and so the canons of the first column have a shadow distance of 9 measures. The middle column has a shadow distance of 6 measures, and the last column has a shadow distance of 3 measures. Unlike the 2 previous canons that we looked at, this canon has shadow distances that are equal to distances of entrance in our table, and so this will change our analysis. First and foremost, though, we need to check that the canons at 3 measures distance repeat correctly. P and R1 is a canon at a distance of 3 measures, and the double constraint occurs when the material in the red box must work above the orange box in measures 10 through 12 and below the blue box in measures 13 through 15. This requires double shifting counterpoint to determine the placement of the imaginary voice. In this case, the imaginary voice moves mostly in parallel thirds with the pre-composed material in the orange box. However, we are not done with the analysis of the first column of canons. Since the combinations at 3 measures distance must also work at a 9-measure shadow distance, and the P and R3 combination must also work at a distance of 3 measures, we can view the red P and R3 combination as yet another derivative of the first column. In other words, if we start with the bass voice leading and the soprano following, then we can view this combination as a canon at a distance of 3 measures, not 9. This is a canon at the upper fourth and 2 octaves, which means N equals negative 17 steps of the scale. Negative 17 minus 1 is negative 18. Which means that the original combination, P and R1, must be composed according to the rules of JV equals negative 18, which is effectively invertible counterpoint at the 12th. For the second column, we have a canon whose distance of entrance and shadow distance are the same at 6 measures. If we try to apply our colored box analysis to the P and R2 combination, we see that there are only 2 colors for the boxes. The material in the orange box must be composed so as to work both above and below the blue box. We can think of the original form of this combination as an original, and the shadow distance version of the canon as a derivative subject to vertical shifting counterpoint. The original canon has an interval of entrance at the lower 10th, so m equals 9, and the derivative shadow version must work as a canon at the upper 10th, where n equals negative 9. Negative 9 minus 9 is negative 18, so this combination must also work under the same vertical shift index as the combinations at a distance of 3 measures. In general, when the distance of entrance of a canon and its shadow distance are equal, the resulting symmetrical vertical shift index can be given as negative 2 times the original distance of entrance. Looking back on Mozart's canon as a whole, we can appreciate the economy of design in its pre-compositional planning. The entire 4-voice infinite canon will work as long as Mozart composes the P and R1 combination and the P and R2 combination in invertible counterpoint at the 12th, which is basically to say that he is treating the interval of a 6th as a dissonance in those combinations, since it will invert into a dissonant 7th somewhere later in the canon. In summary, each combination of an infinite canon has both a distance of entrance and a shadow distance of entrance. These 2 durations will sum to the duration between the repeat signs, what I was earlier calling the body of an infinite canon. Getting both distances to work is what I would call the problem of the repeat. The problem of the repeat only needs to be solved once per distance of entrance. So if a combination in one of the columns from our table of entrances successfully repeats, then the others will too, and their shadow distances will also work. Each combination will then fall into one of 3 categories. If a combination has a shadow distance different from the distances of entrance in the table, horizontal or double shifting counterpoint must be used to solve the problem of the repeat. This is the most common situation, and we saw it in the Beethoven and Haydn examples. If a combination has a shadow distance that is the same as one of the distances of entrance in the table, those combinations should be treated as part of the same column, and therefore vertical shifting counterpoint should be used to solve the problem of the repeat. And finally, if a combination has a shadow distance equal to its own distance of entrance, then it will have a symmetrical vertical shift index equal to negative 2 times its interval of entrance. I will leave you with 2 3-voice infinite canons that you can use for practice analysis. Ultimately, though, the best practice is to compose such a canon for yourself.